Imagine tossing a stone into a quiet pond. The ripples just spread out, completely invisible in the air, until they hit a super sensitive underwater sensor that, instantly translates those physical waves into a jolt of electricity.
Right, which is essentially the magic of human hearing, right? Taking invisible pressure waves in the air and, well, turning them into brain waves.
Exactly. So, welcome to this deep dive where we invite you to explore the fascinating mechanics of how we actually hear.
And since the system is so beautifully intricate, we're adopting some brief roles today. I will be your lecturer, sort of guiding us through the mechanics.
Yeah, and I am happily playing the role of the curious student today. I'll be asking questions to, emphasize the key concepts for you. So
Hmm.
our material today is section 5.4 of chapter 5 from Psychology 2E.
Right.
And to really understand hearing, we first have to trace how a physical vibration in the air actually gets inside our heads.
Right. So let's start with the anatomy. It begins when a sound wave hits the outer ear, specifically that fleshy part called the pinna. And then the wave travels down the auditory canal to the eardrum, causing it to vibrate. That vibration then moves three tiny bones in the middle ear, the malleus, the incus, and the stapes.
Okay, let's unpack this because, it sounds like a biological Rube Goldberg machine.
Yeah.
Why do we need three tiny bones just to pass along a vibration?
Well, it's really all about amplification.
Mm.
These bones act as this ingenious lever system. The final bone, the stapes, presses into a thin membrane on the cochlea called the oval window.
Right, the cochlea is the snail-shaped part.
Exactly, yes. And it's filled with a dense fluid. So it takes a lot more force to move that fluid than it does to move air. The bones basically amplify the tiny air vibrations so they can, physically slosh that fluid around.
Oh, got it. So the fluid moves, and then what happens?
Inside that cochlea is a strip called the basilar membrane, and it's embedded with these tiny hair cells. When the fluid waves wash over them, the hair cells bend.
Which creates the signal.
Yes, that physical bending opens up chemical channels that finally generate the electrical neural impulse.
But if it's all just one long chain of, mechanical vibrations moving fluid, how do we distinguish a low, rumbling bass guitar from a really high-pitched whistle?
So that's where the brain's decoding comes in. Section 5.4 details two main theories for pitch perception. The first is the temporal theory, which argues that a neuron's firing rate simply matches the frequency of the sound wave.
Meaning, a 500 hertz tone makes the neuron fire 500 times a second.
Exactly.
Wait, but the textbook says neurons have a physical speed limit, don't they? Because of how their chemical channels reset, they can't possibly fire fast enough to match, say, a 10,000 hertz pitch. The biology just can't keep up.
That's a great catch. That physical limit is exactly why the brain needs a backup plan, which brings us to the place theory.
Yeah, place theory.
Yeah, the textbook suggests different physical locations on the basilar membrane respond to different pitches. So the base of the membrane is stiffer and responds best to high frequencies, while the flexible tip responds to low frequencies.
So the brain knows the pitch based on where the signal is coming from on the membrane.
Precisely. And in reality, both systems work together. Up to about 4,000 hertz, both the firing rate and the location cues contribute.
But for the highest pitches,
For the absolute highest pitches, those location cues take over entirely.
here's where it gets really interesting to me, honestly, because knowing what we hear is only half the battle. If you're out in the wild, you need to know exactly where that sound is coming from.
Right, localizing sound is basically perceiving depth, but with our ears.
Hmm.
The auditory system uses monaural or one-eared cues to tell if a sound is above, below, in front, or behind us.
That's the pinna again, right?
Yes, the unique ridges of your pinna actually bounce and alter the sound waves differently depending on their vertical angle.
Okay, so vertical is handled by the shape of the ear. But for horizontal locations, I'm assuming having two ears is the key.
Yes, those are binaural cues. If a sound comes from your right, it reaches your right ear a fraction of a millisecond faster than your left. Plus, it's slightly louder in your right ear because your own head physically absorbs and muffles the sound wave before it reaches the left side.
So the brain is basically doing split-second math, constantly calculating these microsecond delays and tiny volume drops between our ears.
Yeah, it's incredible.
That is wild. But because this mechanical chain is so complex, there are distinct ways it can break down, right?
Unfortunately, yes. Conductive hearing loss is a mechanical failure, like a problem with the eardrum or those lever action bones.
And that's what hearing aids are for.
Right, they blast amplified sound waves to just force those vibrations through.
But if the breakdown is neural, like the hair cells in the cochlea failing, that's sensorineural hearing loss.
Correct. Conditions like Meniere's disease fall into this category. Standard hearing aids won't fix a neural failure, but cochlear implants can sometimes bypass the damaged mechanics.
They directly stimulate the auditory nerve with electricity, right?
All right.
It's worth noting how communities using American Sign Language view this. The textbook points out that for many individuals, deafness isn't a failure that needs fixing.
Right.
They highly value continuing their rich cultural traditions over medical interventions like cochlear implants, which really shows that communication goes far beyond just mechanics.
It's a very vital perspective to include.
Yeah.
The human experience of sound and the absence of it shapes entire communities.
So what does this all mean for you? We've traced the incredible journey from a simple pressure wave to a deeply meaningful neural signal.
It really is a marvel.
It is. But consider this. If our brains evolved to constantly calculate these microsecond timing differences between our ears to map our environment, how might modern habits, like wearing noise-canceling earbuds all day, alter your brain's spatial awareness over time?
Oh, that's fascinating.
Yeah, something to chew on the next time you plug in.